All right. Hi, everyone. This is something I've wanted to do for a long time, ever since I made this presentation, which was originally much shorter and for a job interview. Yeah, basically, I wanted to go over the liquid rocket engine that we made in 2024. It was called Borealis. And I wanted to kind of give an overview of the design and talk about all of the different aspects of it, because I think that our final report was a bit lacking in details, and I'm just imagining in like 2 years or whatever, everyone on the team will have forgotten about what we did. And as well, this is probably pretty helpful for other teams if this ends up getting shared publicly. I'm Thomas. I was the propulsion lead for this year. I'm not anymore, but for this I was. Obviously, lots of other people worked on the project as well. Basically, I just want to give a quick overview of the project for people who aren't familiar with what the goal of the rocket was for 2024. I'll talk about the combustion chamber design, talk about the injectors, give a bit of an overview of the fluid system, and I've thrown in some videos as well, just for obviously because videos are cool. That was the background of this picture is the whole team in 2024 with the rocket. So that should give you a pretty good sense of scale. 6-inch diameter sounding rocket. What was the point of the project? Well, we wanted to be, we were the first Canadian student team to fly a liquid rocket engine, which was pretty cool. It was a passively stabilized sounding rocket. We competed in Launch Canada 2024. And the goal was to fly to 20,000 feet. The rocket had a lot of other cool stuff that's not propulsion. I put a couple pictures down below, but you can see there's air brakes. There was also a pretty nifty reefed recovery system that performed not quite as well as maybe we would have hoped, but was cool. And also we had basically all custom electronic stack on the rocket, custom antennas for live telemetry and bunch of other cool stuff, but I'm not going to talk about that. You'll have to go get in contact with other people on my team to learn about the rest of that stuff. Design philosophy of the rocket. We had to finish it in a year. So we flew a hybrid in 2023 at Spaceport America. And then I took over in about August of 2023, and that's when we really started doing work on this liquid. And obviously it flew in August 2024, so we had about a year to do it. And so in order to do that, we had to get to testing as soon as possible. So a lot of the initial stuff that we were testing was really bare bones just to make it happen. And we worked pretty much on just getting a working prototype, and there wasn't a lot of extreme optimization that happened. And there was some desire to try interesting ideas and have fun. We didn't always pick necessarily what like the most efficient or the most optimal solution was. Sometimes there were things that people just wanted to try that we ended up doing. Just to kind of give a brief overview of the engine performance, aiming for 8 kilonewtons of peak thrust with 6 kilonewton steady state thrust. Specific impulse of about 190 seconds. Now, I say about because specific impulse for these blowdown liquids is quite hard. You can't really get a good instantaneous specific impulse because we don't have a good way to measure mass flow rate into the engine, which makes this a bit hard. But generally, I got the specific impulse numbers by taking the total impulse and dividing it by the total amount of propellant that we put into the rocket, which doesn't necessarily give you a super great idea of your combustion performance because there's residuals and things like that, but it does give you a pretty decent effective specific impulse that you can use for, if you wanted to calculate vehicle delta V, for example, sort of an average. Burn duration was about 5 seconds of liquid nitrous combustion. OF ratio about 4. Combined mass flow rate is about 3 kilograms a second. You might notice that number doesn't really line up with the peak thrust, and there's a few reasons for that. But it was sort of designed for that at assuming a steady state flow, which we didn't necessarily always have. Chamber pressure of 400 psi nominally. So propellants were nitrous oxide and ethanol. Nitrous oxide is by far the best amateur liquid rocket propellant. you're going to do amateur liquid rockets, you should generally use nitrous oxide unless you have a really good reason to use something else. Something else generally being peroxide or LOX. Those are really your only other two options. Nitrous oxide is obviously the easiest to use because it self-pressurizes. The vapor pressure is anywhere between 500 and 1,000 psi, depending on how hot it is outside, or how hot you heat the nitrous to. And so, you can basically use that to run your engine pressure fed without needing regulators and a COPV or whatever it might be. So it has much better performance than any other option once you factor in how much dry mass is required to pressurize everything else. And we used ethanol as fuel. You could use any alcohol or any real room temperature hydrocarbon. We just used ethanol because we could get it from chem stores and it's easy. Non-toxic, evaporates. For pressurization, like I said, we use the vapor pressure of the nitrous oxide, and then the fuel tank is pressurized by a piston. So the nitrous oxide actually pushes through an aluminum piston onto the fuel and pushes the fuel out of the tank as well. So like positive expulsion style. Combustion chamber was ablatively cooled. Ignition is done with a solid propellant puck. And all of the fluid control on the rocket was done with custom valves that are piloted with low pressure nitrogen gas. Starting with the combustion chamber, just give a bit of an overview of the design. And as well as I go through this, I'm going to try to talk about things that I think were good and things that I think were not so good. So hopefully you can learn from what we did. So combustion chamber, it's a bolted tube with obviously bolted closure, nozzle retainer at one end, is aluminum, and the injector bulkhead with the injector on it at the other end. In terms of ignition, like I said, we used a solid propellant igniter. Basically, it's just epoxy and, in fact, it is just epoxy and potassium nitrate. We don't add any like burn rate modifiers. Like if you look up the RNX recipe on Richard Naka's website, which is where we got it from, we don't need the burn rate modifiers because we're not, obviously aren't trying to burn it super quickly. It's just a source of heat. Placed it pretty close to the injector to make sure that the engine lights. And generally, people will tell you that solid puck igniters are not good, or that they're likely to get blown out by the nitrous. And that's true unless you make them big enough. So this thing is about 1 inch long, so it's a lot of burning surface area, and it you'll see in the static fire videos, but it basically fills the entire combustion chamber with fire. And so it basically guarantees that your engine is going to light. To light the RNX, there's a little nichrome wire that's just wrapped in there, and then you just put a bunch of amps through it, and the nichrome heats up and gets it started. The wire is cast in right as we make it, which on a solid motor would be extremely dangerous. Don't do that on a solid. But on a liquid, if the igniter goes off, it never builds up any pressure, so it's not really dangerous. It's just a toxic fume campfire, basically. The nozzle is a giant chunk of graphite. It's about 5 inches in diameter, I think, at the biggest point. People will also tell you that big chunks of graphite are bad, and to some extent I agree. I think the reason that we get away with it is that the graphite doesn't hang out very far. When the graphite's in tension, it struggles a lot, but most of the graphite in this nozzle is in compression. The only bit that's sort of loaded in tension is the little bit that hangs out. I would be willing to bet that if you doubled the distance that the nozzle hangs out the back, it would be very liable to cracking. In the future, it might be worth looking at using a smaller piece of graphite. Also, just because graphite is heavy, all of the graphite that you see, like that's not like right at the kind of throat, doesn't really need to be graphite and is just extra weight. Then we had 2 layers of COTS phenolic. The reason we had 2 layers was just because the hybrid the year before had 2 layers of phenolic, and so we just cast into the smaller layer and used the bigger layer to bridge the gap so that we had the same size tube. In the future, you only need 1 layer of phenolic casting tube, or you could even bond directly to the aluminum, although that would make your case single use, so I wouldn't recommend that. You'll notice there's also this phenolic piece, this phenolic piece at the back. Phenolic piece is to isolate the graphite from the aluminum. Don't let the graphite touch the aluminum because the graphite can get really hot, but it also transfers the heat to whatever's behind it. And you'll notice the case is pretty thin of the engine. And then obviously cast into the phenolic liners is custom ablative, which was made of epoxy and microballoons and boric acid. If you know about half-cat chamber safe, that's basically what it is. And the liner is split. The reason there's a split in the liner, and you can see the split here, is that to cast the igniter, you need to cast it directly into the top liner section. And then the split kind of has the joints offset from each other to sort of reduce the likelihood that gas just blows by both of them. And every joint in the combustion chamber has RTV as seals, and then including the head end of the chamber. And then at the back, there's 2 O-rings as well. And obviously, there's an O-ring on the injector bulkhead. Yeah, that's basically it for the combustion chamber. We did do a bunch of work to try to characterize the ablatives, and we tested a whole bunch of materials and ended up on a final formula of epoxy, boric acid, and microballoons. We made this test setup to test ablatives, and the way it worked basically is you had an oxyacetylene torch blasting little puck samples that we casted, and there was a thermocouple on the backside, and we basically ran the torch for a consistent amount of time on each sample, one after another, and measured basically how hot the thermocouple got. Now, the problem with this, and some of you may already be thinking about this, is that this is really good for testing how conductive the ablatives are, but it doesn't do a very good job of testing for how durable the ablative is. So the ablative both has to not conduct the heat back to the wall, but more importantly than how conductive it is, it needs to hold up to the combustion gas and not erode too quickly. And this doesn't really test erosion at all. So if I were to do this again, I don't think this testing was actually super representative or super helpful. And if I was to make any changes to the formula, what I would probably look at doing first is adding some sort of fiber matrix, so either carbon or fiberglass or silica fibers. Try to orient them sort of like in a tube shape, like get sleeving or something, because that would massively increase the mechanical strength of the ablatives. The testing setup was pretty good at getting consistent results. Like the black and the gray and the brown here were the same recipe. We made 2 of the same recipes sometimes, and those 2 were the same and performed basically identically. As well, the dark green and this kind of brown color here were also the same recipe. And so I think we were getting consistent temperature results out of this, but we weren't getting really any good idea of the mechanical properties of the ablatives under temperature, which is also super important. So yeah, kind of getting into the injector design, which is obviously the heart of these pressure-fed liquid engines since they don't have pumps. This is probably the hardest part. We looked at a bunch of different things. We looked at pintle injectors. The team had actually previously tried pintle injectors twice, and both of them had not worked for different reasons. The first one hard started and exploded, and the second one had terrible mixing and a very, very lopsided chamber, and so it didn't really light properly. Pintles are good because they're known to be stable, but we had a lot of problems getting the annulus to be even and getting even flow around the annulus. And to get good mixing out of pintles, I think you need really small fuel holes, which made them kind of bad. Also looked at impinging injectors. To be completely honest, if we were going for just the simplest thing to get working, we probably would have done some sort of impinging injector. The reason that we didn't do that is mostly because there was another kind of injector that I thought would be more fun to do. I'll get to that in a second. Did coaxial shear. Coaxial shear injectors are also pretty good. I think you can get good mixing out of them, although I know people have had issues with them. I think if you use enough elements and you vaporize the nitrous before it reaches the part where it interfaces with the fuel, you can get a pretty good velocity ratio. But it required a lot of needles, and I was not super keen on trying to bond all those needles accurately. So what we ended up going with was coaxial swirl injectors. This is mostly because it let us have a larger annulus compared to other designs, because you can control the flow rate with like the annular holes instead of having the annulus dimensions itself set your flow rate. And obviously, if we need to change the thrust later, you can do that pretty easily by just adding more elements to the injector plate. Of course, the downsides here is that machining them is not super easy. And there is a bunch of interpropellant seals that need to be made. They are static seals, but they still need to be made somehow. And we had a lot of issues with that in the end. Did a bunch of prototyping. This was the first thing we did on the engine. You can see basically the way we designed the swirlers. I didn't think that I could machine a fuel swirler that was small enough to be in the center. So we bought these spray elements from McMaster Car, and that was the central fuel post. And then around it, we made these oxidizer annuluses. And you can see there I'm drilling a tangential hole on the mill in the center picture. And then on the right-hand side, the very first thing that I did was try to make a swirl element that would make a swirl, and I tested it in the sink in the bay. And that actually worked pretty well. So that's kind of why we proceeded with this. Basically, looking a little bit more closely at the design and kind of how I picked the dimensions. The fuel spray angle was given by the geometry. I picked the McMaster element with the widest spray cone, which I think was supposed to be 120 degrees. So the CAD model doesn't really have it, but the spray angle was supposed to be actually quite large. The oxidizer swirl angle was just determined experimentally by how far offset the hole was from the kind of exit plane. We used the NPT threads, at least in the initial design. The NPT threads of the McMaster element with the hex the hex was turned off on the lathe, but the NPT threads were left, and we used them to locate the fuel post in the center of the element. The fuel element was recessed because research showed that it provided better stability and combustion efficiency. The overall height of the element was set by how long the McMaster Car fuel sprayer was. And the whole thing is made of brass because the McMaster elements were brass, and I didn't want to have to deal with joining unlike materials. We were planning to braze the injectors, and I wanted them to be all like materials. Then the plates in the injector were also made of brass, again, because it's easier to join them together. Looking a little bit at kind of what we did for the injector manifold, the oxidizer comes down the middle, actually, and then kind of enters the element sideways. And then the fuel comes in offset on one side. And then opposite that, we had a spot for a fuel pressure transducer. That didn't make it to flight, but it was there in the first static fire because I wanted to know how much pressure drop there was across this manifold and across the feed line as well. One thing to note here, there's two O-rings everywhere where fuel and oxidizer are together. That's because the interpropellant seals, you always basically want to have two O-rings. And then, to get a combustion pressure transducer through this bulkhead, kind of snuck it around the side, and then I milled slots that dodged the ablative so that the hot gas could kind of leak around the ablative and up to the pressure transducer. In terms of seals in the injector, like I said, there's two O-rings for the interpropellant seals. At the interface with the combustion chamber, the thread there that holds the element in place is actually completely unsealed. And I did this because I didn't think there was a ton of reason that joint needed to have another joining operation. Basically, my thought process was that the leak rate through the threads would be pretty minimal, and it's just adding more oxidizer to an annulus that's already spraying oxidizer. So as long as we characterized it in our cold flows, I didn't think it was necessary to make that seal. And that made it nice because it meant that we only had one plate that needed to be lined up super precisely to get the solder joints. And we used silver solder paste to try to do the solder at those joints. The NPT thread didn't have Teflon tape or anything on it. We filled it up with solder before threading it on, and loaded the top with solder as well to try to seal that off. And we did test all of the seals to, at least the solder joints, to 1.5 times operating pressure by, we had some plugs that would go into into this part of the fuel swirler, into the top part, so that you could pressurize the fuel side, and have the oxidizer side unpressurized to make sure that you weren't leaking super quickly. All the O-rings on the rocket are just Buna and rubber. There's not really a point in using a fancier rubber, because it's not necessarily, the nitrous is not super likely to decompose with it, and the seal lifetime is like, it gets installed, tested, and then immediately taken apart. So don't need to have like the best chemical compatibility in the world. It just has to be good enough to last for a day or two usually. So yeah, to characterize the injectors, we made single injector elements, so that we didn't have to machine full plates every time. Basically, we tried to measure mass flow rate by hanging the tank from a load cell, and then the manifold pressure of the injectors was measured with a pressure transducer, and obviously the same on the fuel side. One thing that maybe wasn't so good about the setup is that I had the fuel coming straight down the center, like straight in, whereas in flight, often it's kind of wrapping from the side and then coming down. But it ended up being pretty close on the fuel side, our characterization, so I don't think it actually mattered too much. So cold flows were conducted with water on the fuel side as a substitute for ethanol, because they're both single-phase incompressible. Spray angle was just visually analyzed, and obviously we're going into atmosphere, but we would do it at the tank pressure was the expected like delta pressure between the tank and the combustion chamber, and then obviously you can adjust for density. It just scales with the square root, basically. You can see obviously when we start the flow, the water hammer really shakes the tank around, but there's actually pretty consistent and good data from these fuel cold flows that actually gave a pretty good amount of confidence in the CD characterization of these orifices. On the nitrous side, it's a lot more complicated. You can't really represent nitrous with just single-phase incompressible, because it obviously, as it starts dropping pressure across the orifice, it switches into two-phase flow, so it starts boiling and gas bubbles and vapor starts forming. There's a couple different models for this. In the description of this video, I'll put a link to a paper by a guy named Benjamin Waxman, who has an excellent, much better than I could do, thesis about this exact thing and kind of all of these different models. But basically, we use 3 models: single-phase incompressible, a homogeneous equilibrium model, and a Dyer model. Dyer is basically just a weighted average between the two of them. And basically, what this graph underneath is getting at, and for reference, coefficient here is everything that's not CDA. I've basically separated CDA out, and then you have CDA, and then everything past that is kind of what changes with the model. And this is at a fixed tank pressure. So I've said that the tank pressure here is 600 or 750 psi or whatever it is, and then it's just looking at the pressure drop, basically. And what you can see is that single-phase incompressible just continues to rise as the pressure drop increases, whereas the Dyer model kind of arcs over, and at about 300 to 400 psi pressure drop, there's not really much extra flow rate, and homogeneous equilibrium arcs over much quicker. And the reason there's this horizontal line is because you're basically when it reaches its peak, you're supposed to assume that the flow is what's called critical flow or choked flow, where basically you've hit a maximum amount of flow rate, and there's enough vaporization that it kind of chokes up, sort of almost like a cavitating venturi, if you know what those are. So we didn't really know which one of these models was going to be the best, but we knew that homogeneous equilibrium generally underpredicted from data from the hybrid. So we're really looking at single-phase incompressible and Dyer model. We did cold flows with both water and CO2 to try to kind of figure out what the coefficients would have been. But unfortunately, Benjamin Waxman's data really indicated that the models can't really accurately predict the critical flow with the short holes, the short nitrous holes that we had, because they're through the annulus, the LD, so the length to diameter ratio of the hole is very, very, very small. So to make sure the engine was going to be okay in the first static fire, basically what I did was I took an average of the Dyer and the single-phase incompressible models, and I used that to size the nozzle. And then I designed the engine so that if for some reason there really was no two-phase behavior because the holes were so short, there just wasn't enough time for any vaporization to occur. If the flow rate was excessive, the injector delta P, so that the pressure drop across the injector would still be at a safe value. So it would still be high enough that we were confident the engine wasn't going to hard start. The other things, the spray angles on the injectors weren't really as wide as we intended them to be. I was kind of imagining sort of a 45-degree cone for the injectors, but especially as you increase the pressure drop up to 300, 400 psi, which is what we were planning for in flight on the engine, especially the fuel elements really narrowed in, and as well, the CO2 basically didn't spray out in a cone. And I think the reason the CO2 didn't really spray out in a cone, the CO2 is the leftmost image here. You can see it's basically just coming down straight. I think the reason the CO2 didn't spray out in a cone is because there's so much vaporization in the annulus, that so much turbulence, that it just, any of the radial momentum we were giving the flow was just canceled out by that. The image on the right here is a combined cold flow of both sides of the injector with water. You can kind of see faintly the fuel cone in the middle. But you can see that at 400 psi delta P or whatever this was with water, the oxidizer swirler was giving a nice big angle. But the same swirler on the left-hand side, it's the same element with CO2, with the two-phase flow, just doesn't really swirl at all. But this was really only an efficiency concern. This wasn't going to affect much. So we decided to do the first static fire and reevaluate if the efficiency was going to be a problem after that. There was a bunch of integration issues trying to put this injector together. The number one issue being that the solder joints were extremely leaky. You can kind of see in the image on the right here, there's a few little pinholes. Those were just spewing water when we did hydrostatic testing. We were able to get it down to a quote-unquote acceptable leak rate by spot fixing, but we did static fire these injectors with a known leak between the fuel and oxidizer manifold. It was pretty small. With water, it was maybe losing 100 psi a second. So that would be equivalent to maybe a couple gas bubbles of nitrous bubbling through into the fuel manifold over the course of a 5-second burn. And the reason I went with this was because at this point, exams were coming up at the end of the first term, and everyone was going to go on break for the holidays anyways. So figured we may as well just test it. If it dies, we could reevaluate our manufacturing methods after anyways. And there's actually a bunch of research that shows that you could actually potentially even premix your nitrous and your fuel before you even send it into the chamber. So I wasn't super worried. The reason that we ended up with this, even though none of our single elements had these solder joint issues, is basically the single elements were really easy to heat up evenly with a torch and get the solder to flow. But on the big, much bigger plate, it was really, really hard to get it to heat up evenly, and so the solder was kind of bubbling all over the place. And because we had more than one element, it was quite hard to get all of them lined up nicely. And so the gap around the elements was extremely uneven. And so that basically meant that in some places the solder would flow and melt through really nicely, and in other places it had a really hard time filling the gaps, basically. There's a picture of me with maybe the worst hair you've ever seen. with all of the disassembled parts of the engine before the first static fire. And on the top right, there's a picture of the injector kind of integrated, and you can see there's the 2 pressure transducer ports as well. We had 2 of them in case one of them died. We didn't pack them with grease or anything. They were just stood off with thin 1/8-inch tube from the combustion chamber. And I have a video here of the first static fire. It's going to
Injector in 5, 4, 3, 2, 1. All right. Open DA3.
So yeah, that was pretty okay. The engine didn't explode, which was great. One thing to note with the first static fire, the fuel tank was pressurized with nitrogen. We used 2 different tanks because we hadn't built the piston tanks yet, so it's not perfectly representative of flight, but we operated it in blowdown with about 30% of the tank being fuel and the rest being nitrogen. And you can see on the right-hand side here, with aux pressure in green and fuel pressure in orange, that they followed together pretty closely for the burn, which was basically exactly what I was hoping would happen. So the calculated ISP of the static fire was about 185 seconds, peak thrust of 6.4 kilonewtons, which was a little bit below what I had wanted. But overall, it was pretty good. You might have noticed the shutdown was really rough. The chamber basically blew out. You would expect normally that it sort of be a tail-off phase here with the vapor nitrous. But the chamber basically blew out as soon as the liquid nitrous ran out, and then sort of flashed back and reignited. Also notice that there's a thrust spike at the start of the burn. That's sort of what I was talking about steady state. The thrust spike is sort of a little hard start caused by... I think the probable cause is just that there's a little bit of a delay between when the propellants start flowing and when the chamber actually comes up to pressure, because we just slam the valves all the way open at the same time. And so that sort of leads to a spike. As well, you can also see it exists on the tank pressures, albeit smaller. So the other probable cause is that there's sort of this lag. They call it like boil-off delay, where the nitrous takes a second to start evaporating, and so you actually lose probably 100 to 150 psi of tank pressure in the first quarter second of your burn due to this phenomenon. But yeah, overall we were pretty close to our predicted values everywhere. The OF ratio was a little bit fuel rich. We lost a little bit of nitrous flow rate. It was a bit lower than expected. And general pressure was basically right on, but we were kind of significantly below the thrust that we predicted. We were saved by the thrust spike, but the steady state thrust value was a little bit lower than what I had predicted. The other big problem with the static fire was that the injectors just completely melted. The interesting thing here is that the thrust curve looked basically normal, which basically exactly as you would expect for a nitrous blowdown liquid, which implies to me that these didn't melt in the middle of the burn, because right here you can see these sides are supposed to have small orifices, not have the entire side be melted open. And so I have strong reason to believe that it was at the blowback or after that from heat soak. Or something that these injectors melted through. I think it was probably when the flame reattached to the combustion chamber. But causes for failure or potential causes, we still don't know exactly what happened. The potential root causes were the shutdown sequence was bad. The fix to kind of trying to do that was that we were just going to cut the fuel off, have the fuel run out before the nitrous. So ignore the vapor phase of the nitrous and just have the fuel cut off right before the nitrous runs out in the tank. I also think it's pretty probable that the leaks in the manifold meant that when the flame reattached, there was like combustion in the manifold. So we did change the joint design for the next static fire, and we'll talk about that in a bit. The other issue here is that obviously the sleeves of the injectors are not super thick, but we didn't really have a way to fix that because we couldn't thicken them without getting new cold flow data on the orifices, and we didn't have the time in the winter to do that testing. So the thing that I changed was I made the recess depth that the fuel element was recessed into the oxidizer sleeve. I reduced that depth to try to get the combustion to happen further down in the chamber, which would hopefully reduce the heat load. The other probable cause, you may have heard the engine kind of squeals a little bit, has a little bit of a screech instability. Combustion instabilities are known to increase heat flux at the injector, depending on the mode. And in this case, we just ignored it because combustion stability analysis and testing is beyond our means as an amateur student team. So just hoped that the other fixes would solve the problem. The other thing that I ended up doing is changing the faceplate to brass. It's not shown here because this is an old screenshot, but it ended up being all brass. And brass melts significantly at a significantly higher temperature than aluminum and doesn't conduct the heat. Or I guess it does, but it can absorb a higher heat load because it's massively denser. So there's also some thought that we could heat sink more heat into a brass faceplate. So changed it so that all of the injector seals were shrink fits. So I basically machined them as an interference fit and then shrunk them with liquid nitrogen and pressed everything together. This was a interesting idea. I would not recommend doing it, and I'll explain why later. So there's no more solder joints at all. Every joint was just a shrink fit, an interference fit that was tight enough to make a seal. The nitrous mass flow rate was increased from 2 to 2.5 kilograms a second by adding an extra hole to the injector elements. So the sleeve now had 5 holes into it instead of 4. And we changed the packaging significantly for flight. You can see how much smaller the thing got. The mass was reduced by 40%, and that's after adding that mass is after changing the faceplate to brass, which significantly increased the weight. One of the things with the sort of shrunk fit injectors is that obviously we had to press each of them in individually. And so at the injector face, we couldn't have threads anymore. This original aluminum design had basically you would press all of the interpropellant joints, so the brass into the brass, and then all 6 of these were supposed to be one press fit that was going to go after. Why I thought that you could tolerance that, I have no idea, but I made the first plate and pressed them in and knew that it would be impossible to make a press fit that would fit onto it. So that ended up being a brass plate, and we ended up actually doing some torch brazing, not soldering, by one of the welders at the university. He soldered those joints or brazed those joints at a much higher temperature for us. The design, in order to get those kind of weight optimization improvements, it ended up with this asymmetrical flange. This was also because we needed spots for the thrust transfer structure to mount. So the fuel comes in offset completely from all of the elements and then flows around to them. And the flange also allowed the oxidizer valve to be mounted directly to the injector. So there's no tube run between them. I did a bunch of fancy FEA on that with the bolts simulated. This is basically just a note about FEA. This engine was designed almost entirely without computer simulations. This is the only part, other than the tank bulkheads, that I actually did FEA on. And everything else was hand calculated. And the reason this was done with FEA, it didn't even really need to be done with FEA. The main reason was because I wanted to see if there was different stress in the bolts, which definitely wasn't required given how many bolts we had and the safety factor that was used. But I wanted to learn how to do multi-body FEA with bolts. So this was mostly learning motivated, definitely not required. And I don't think for the style of amateur liquids, that most people are building, you have to really do any kind of advanced computer simulation. And often I think it's just a waste of time, unless it's something like this where you want to learn. We did a flight qualification static fire. You can see the thrust was increased significantly. We had about an 8,000 kilonewton peak, and then 6,000 kilonewtons, or 6,000 newtons, 6 kilonewtons from there. You can see that the thrust cuts off extremely sharply. That's because that's where the fuel piston bottomed out, and there's a little bit of nitrous left over, a little bit of liquid nitrous left over that kind of threw out the chamber. For flight, we adjusted the propellant loads just a little bit to try to get those to shut off closer to the same time. These little spikes at the end were a little bit of popping. I think it was just nitrous vapors decomposing against the chamber liner before we started the nitrogen purge, which probably started right about here, just a couple seconds after those occurred. After the qual static fire, the injectors didn't melt, which was great. But the first cold flow we did during wet dress rehearsals, after that, one of the central fuel posts popped out of the injector. And this is why I don't think you should do press fit injectors, because I think that any kind of high frequency combustion instability is going to put many, many vibrational cycles on those. And that, combined with the potentially elevated temperatures, just means that it's really likely that the stress that's holding your press fit together is likely to relieve itself very quickly. So we ended up brazing the injectors. Why we didn't just braze them all from the start, the reason is that there was a lot of motivation to kind of make them ourselves and not rely on the shop machinists or the shop welders who, like the professionals that the university had to do it for us. But at this point, we were close enough to flight that we didn't have time to remake this. So I put it on the CNC and put grooves into it, and then we filled them up with braze alloy and got one of the shop welders to do a good job brazing for us. Being careful, obviously, not to get braze down into the fuel posts. One thing with the static fire, we didn't quite get as much of an increase in oxidizer flow as we were expecting. It did increase, but not quite by the full 20% that I thought, which somewhat suggested that the gas flow in the annulus was at least partially limiting the flow rate, and that the annulus area was kind of partially contributing to that. The other thing that happened is after the static fire, the fuel element CDA shifted. During our wet dress rehearsals, I just took a second to analyze the data from them just to check the orifice CDs again. And I suspect that it's either soot from the brazing or from the static fire that got in them. But it pushed the OF ratio to 4.25, which is closer to stoichiometric. So we actually probably ran slightly more efficient in flight than we did in static fire. Didn't have a huge effect on thrust because the total mass flow, the fuel is a small part of the mass flow rate, and the change in CD was a small part of that small part. So yeah, that was basically the combustion chamber. We'll talk a little bit about the fluid system from here on out. Just start with the P&ID. So everything sort of to the left of where my mouse is right now is just fill stuff, GSE. There's a panel for nitrogen and a panel for loading nitrous. The fuel is loaded manually. But I'll specifically focus on the rocket. The rocket has 4 valves on it. The rocket has, I guess technically 5. The rocket has a fuel main valve and an oxidizer main valve, both of which are pneumatically actuated. It has an oxidizer fill valve that is pneumatically actuated, a oxidizer vent valve that's pneumatically actuated, then there's a manual fuel valve that's used for filling it. There's also, I guess technically a manual nitrogen valve to drain it. There's a pressure relief valve set at 1,000 psi on the oxidizer tank. In terms of sensors, there's a pressure sensor, a pressure transducer on the ox tank, obviously. There's also one on the fuel tank. We debated a lot whether we needed a pressure transducer on the fuel tank, but we left it in there because we wanted to know basically if the piston failed or got stuck. We wanted to know if there was a sudden drop in fuel pressure. There was one pressure transducer on the combustion chamber in flight. There was not enough space to fit two into the section with all the plumbing on the flight vehicle. And then both the oxidizer valve and the fuel valve had magnetic Hall effect sensors. This is mostly just a test to see if we could do it. Or we had done them in the past, and we thought it was good to have them. There wasn't really a ton of reason to have them. But it does give you peace of mind that you know that your injector valves are in the state that you commanded them to be in. But to be completely honest, it's mostly because we could and not so much because they were required to be there. Looking at the propellant tank, this is kind of the bulkhead at the top of the tank. You'll notice that the bulkhead is significantly thinner than the tank wall. That's both because the tank wall has significantly more stress than a kind of a spherical thing. But really the reason is that the tanks were too thick. So that the tank was, I think, 3/16 of an inch thick. At 6-inch diameter, you can use 1/8 inch with nitrous. That would be a change that I would definitely make in the future. However, having it be thicker does have some advantages, like it is better at surviving a hard landing. Maybe some foreshadowing there. Then obviously the fuel tank is in the middle, and you can see the piston there. Notably, the piston had two O-rings, so an O-ring for fuel and an O-ring for oxidizer. And the piston also had two wear rings. The wear rings were added to try to help keep the piston straight and make sure that the aluminum wouldn't kind of dig into the other aluminum, and that it would always be riding on the Teflon PTFE wear rings. The fill bulkhead was pretty interesting. Obviously, significantly less mass optimized than the domed bulkhead at the top of the tank. But a big part of the reason for this is that you may have noticed that the injector takes nitrous down the middle and fuel offset to one side, but the tank has nitrous on the outside and fuel in the middle. So to kind of invert these, we had this sort of crossed manifold drilled thing. And in order to get enough kind of space for a big, there wasn't enough, I didn't want to add more height to the fuel tank. So instead there's like a bunch of drilled nitrous holes that kind of are in a circle to get enough flow area for the nitrous manifold. For all of the nitrous plumbing, we generally followed a fairly oversized flow area rule. So I think it was 3 times was the minimum that we had. This is a pretty just like hand wavy way to make sure that there's no significant pressure drop of nitrous across the feed lines. But if you drop too much pressure across your feed lines, it starts to boil, and that's a big cause for unpredictable flow rates and for feed system coupled combustion instabilities. And we learned that lesson the hard way with the hybrid. If you want easy to predict flow rates, keep your nitrous liquid until the injector and make all of the vaporization happen in the elements. Looking at the main propellant valves, they're both coaxial sleeve valves with knife edge PTFE seals. The PTFE seals used to be machined angled seals, but we changed them to knife edge seals because we were getting a lot of dirt and stuff stuck in the PTFE seals, and they were getting quite deformed, so we had to replace them a lot, and water jetting out circles of PTFE is massively quicker than having to machine angled surfaces for the valves to mate with. Both of these valves have a bias spring that biases them closed. The reason for this is that we'd rather abort by dumping out other valves than these, and there's not really any case where having them go closed is a problem, unless they were to close right after takeoff, but that is pretty unlikely. You'd have to lose all of your pneumatic pressure instantly for them to close fast enough that you aren't at a safe height for the parachute to come out. You can see that the magnet rings are also in there, which were used for the Hall effect sensor. And obviously both of these valves are double acting. There wasn't a ton of reason to have them be double acting, other than it just meant that the springs didn't have to be nearly as large, and we had double acting solenoids. but yeah, obviously the flow paths are shown in red, so the flow is sort of around a central kind of annular flow path. And both of these valves were mounted to a bulkhead. So the oxidizer valve mounted directly to the injector at the combustion chamber, and the fuel valve was mounted directly to the bulkhead, the lower tank bulkhead. So they each only had one run of plumbing coming off them. The fill drain and the vent valve are both very similar. They're both poppet valves. So the fill drain valve has a kind of umbilical and makes a 90-degree turn with a PTFE poppet seat. And it's basically the exact same thing for the vent valve. The vent orifice is directly built into the valve on the vent valve side. And the only difference is that the vent valve also has a spring that biases it towards open, because the vent valve is sort of our like ultimate safety device to make sure that we can always save the tank. Both of these valves are single acting, so the pilot pressure holds them closed, and if you were to vent the pilot pressure or to lose pilot pressure, they would open and abort, which is obviously a good outcome. When you're operating a system like ours where there's not a static vent, it's quite important that you don't get the tank stuck with all of the valves closed, because then you have to potentially pull out the shotgun to shoot the tank, which I say sort of jokingly, but has actually happened multiple times. So yeah, what does this look like all integrated together? This is the section between the bottom of the tank and the top of the combustion chamber. You can see there was really not a lot of room. I had to do a lot of fancy things with plumbing, but you can see the fill dump valve mounted to the bulkhead here, and the fuel valve is here, and the oxidizer valve, you can't even see it, but it is buried behind. And I put some pictures here of some of the kind of fancy plumbing that we did. So to get a fuel fill port accessible and a fuel pressure transducer, this is the tubing stack that ended up coming off the bulkhead, and the way the tubes were routed. And on the right-hand side, you can see the sort of quick disconnect plate. I don't have any good pictures of the quick disconnect, and I'm sorry. It is a remote disconnect, and the way it works, I'll just explain it. This is a swage lock quick connect fitting, and the female side of it was on the ground part of the disconnect. And then at the bottom, this is a machined hole, and you can't see it, but there's actually a female small O-ring in there. And a piece of nylon tube went in to feed the pneumatics into the rocket. The pneumatics were filled through a check valve, so it was just a check valve stopping them from leaking out. Foreshadowing, you shouldn't use check valves for this purpose. This should have been a solenoid, and I'll explain why later. Yeah, basically the way this worked is there was a mechanical actuator that would pull the sleeve back to release the quick connect, and then once the quick connect was released, we'd feed the low pressure 100 psi nitrogen into the quick connect on both sides, and it would just get forced apart by the fluid pressure. The reason we didn't just disconnect it underneath the full nitrous pressure is that it would blow off quite violently, and the O-rings inside would get blown out every time. So it was actuated with just the low pressure nitrogen, and would just sort of pop off. In terms of controlling the engine, and sort of the con-ops, I guess. The fuel is pre-filled with a hand pump. The piston starts bottomed out so that you get as little air trapped in the volume as possible. The nitrous oxide was filled cold by opening vent valve and the fill valve. And we'd filled it colder than the operating pressure, and then the tank was isolated and heated. We had PCBs basically that were just a big resistor that like flexible PCBs that were taped onto the tank to heat it up in case it was cold in Timmins. And we couldn't reach the operational pressure, which was, I think, 800 psi plus minus 15. The aux tank, fuel tank, and pneumatic pressure were all monitored remotely. And the remote disconnect was basically the last thing that would happen before entering terminal count. So we'd disconnect, confirm that all of the pressures were stable, and then count off to starting the igniter. The igniter is operated by reading amps that are flowing through the nichrome coil. You can actually watch to see when the amperage drops out when the coil burns through. But for flight operations, we actually just did it by watching for smoke coming out of the combustion chamber. And as soon as you saw smoke starting to count, the igniters burned for about 30 seconds. So there was lots of time to see the smoke and get the rocket in the air before the igniter would burn out. Both propellant valves were opened at the same time. This was done to avoid the possibility for an electrical failure where one of the valves would open slow or one of the valves wouldn't open at all. So they were both hooked up to the same electrical connection, both solenoids. Or they're both, there was only one solenoid and the pneumatics were connected to both valves. So both valves were controlled simultaneously through one solenoid. Yeah, this is a pretty cool still shot of that rocket taking off. And I have a video here that will play. I'll note here, that's the quick disconnect floating in the air. You can see it bounce around when the rocket takes off. You might have noticed that we had an extremely high thrust to weight ratio. That's on purpose. Having a high thrust to weight ratio is good for keeping your rocket going straight and lets other people put heavy, cool projects into the rocket. I highly recommend that the team continues to keep thrust to weight ratios above 10 as an absolute minimum. No gravity turns, please. So yeah, apogee of the rocket was 19,212 feet. This is almost all due to loading a kilogram less nitrous than we planned on. The nitrous fill level was set with a dip tube that was set the day before launch. And the weather at launch day was significantly hotter than we had planned for. And so the nitrous going into we didn't cool the cylinders as much as they needed to be. So the nitrous going into the rocket was less dense than expected. So we weren't able to fill quite as much as we wanted. The maximum velocity of the rocket was Mach 1.3. Propulsion system performance was almost flawless. The only problem that we had was when the umbilical disconnected, the pneumatics started leaking at about a PSI per second, which was quite disappointing because we had left the pneumatic system pressurized and disconnected the entire time we raised the rocket, which ended up being almost an hour if you include all the photo ops before we reconnected. And we lost maybe 5 psi over that entire time. But of course, as soon as it was time to fly, the check valve or some other fitting immediately decided that it was time to leak. But this is a pretty good example of sort of paranoia because our operations procedure originally called for doing the disconnect far earlier. And maybe like 2 days before launch, I was really stressed about the pneumatic system leaking. And so we moved the disconnect to right at the end, right before launch, which saved our launch attempt. The recovery system performance was definitely less than flawless. We got the drogue out, but the main parachute, which was actually just the drogue parachute, it was a reef system, never disreefed properly. So we hit the ground quite hard. You can see that the oxidizer valve seat is exposed to the air and the fuel feed line is completely bent. The valve sheared clean in half, which is actually pretty crazy. The valve tore right off. And we did end up winning first place in our category at Launch Canada with that. So yeah, I have a bunch of like lessons learned or takeaways that I would say from this project that the team and maybe other people might want to take coming forward. Long holes for nitrous oxide. It's way easier to characterize your engine with cold flows if you have long holes, because the closer you get to longer holes, the closer you can get to just assuming that it will follow the Dyer model, and that if you did a cold flow into atmosphere with CO2 at your tank pressure, the flow rate isn't going to significantly change between that cold flow and your static fire, if it is actually in critical flow. Don't have two-phase flow in your injector. Solder and braze joints suck. Injectors that don't use them are definitely superior. We have been this year, I'm filming this about 6 months after the flight, and this year we tried to do more braze joints, and we've completely given up on them. They're extremely difficult to do well without just having the shop guys do it for you. We had a lot of issues with DAC being spotty during testing. Make sure that you have a good DAC system that gets you the data you need, because it can be extremely hard to do analysis otherwise. Changes early are a lot easier than changes late in the design cycle. There was a couple times where I wanted to change some things, and it was just too late to make those changes. And make sure your testing is actually representative. The whole first static fire fiasco, trying to fix the leaks in the injectors, could have been avoided if we had just tested with a more representative manufacturing sample before proceeding. The system interface requirements were really bad between propulsion and electrical, and there was a lot of issues with the final integration of those harnesses when it came down to it, and sort of how that all worked. And we should have done the integration of the injector section a lot quicker. I'll just skip back to it here. This is really tight. You don't want to design something that's this tight. This was quite difficult to put together. Although it looks really pretty when everything's assembled, it was quite hard to put together. The other thing I'll venture is don't use these push-to-connect fittings for pneumatics. If you're going to have pneumatics, you should use metal fittings, and that also means that you can use a higher pressure. These push-to-connect fittings are really unreliable and were quite difficult to make not leak across the whole pneumatic system. But these solenoids are great. But yeah, don't use these push-to-connect fittings. They're operating so far outside of their design space that they just leak everywhere all the time. And yeah. I guess feel free to leave questions in the comments of the video or whatever. Yeah, I'll leave it there. Hopefully this was kind of a good overview of what we did. Hopefully it answered some of why we did it, and kind of maybe gave you some ideas for what you guys maybe want to do in the future or that. So yeah, thank you for watching.